Hi, today we're going to continue our discussion with the gradient and how it affects vectors in space and surfaces. Now we know in the past couple of videos that the gradient finds the direction of steepest increase. For today's lesson, what we're going to talk about is how does that gradient correlate into three-dimensional surface. Now before we can do that, we got to kind of review level surfaces and how to write the equations of plane. We'll be doing some planes and stuff today. So in the first example here, we want to describe the level surface of this function of this surface here when our function's value is equal to 2. Well, if I set this equal to 2, we would get 2 equals z minus x squared plus y squared plus 3. Now notice this is a three-dimensional surface, and if I simplify this, we would get z equals x squared minus y squared minus 1. And we should recognize this as a hyperbolic paraboloid. If I want to describe the surface here, if I want to describe this function surface, so if I simplify this, we would get 4y squared minus x squared minus z squared equals 9. And we might recognize this as a hyperboloid of two sheets. So let's kind of review how we would graph this. Remember this one, hyperboloid of two sheets right here. The odd one out is, of course, the y-axis. So on the y-axis, we would have our hyperboloid, oh, sorry, two sheets. So I should draw with two sheets here. Let me go and fix that. There we go. So it might look something like this, and don't forget the other side as well. So this is going to be opening up on the y-axis. And you can view that, but the main thing is, since the y is the odd man out, these are both negative, it's going to be opening on the y-axis. So some definitions of the tangent plane and the normal line. So if we know we have a function on a surface, and if that value of the function equals to 0, and that the gradient is not 0, so we don't want the gradient to be 0, then we can say that the plane through P that is normal, remember normal is perpendicular, is called the tangent plane. So basically says that we can find a tangent plane here. And also that we can find a normal line. Now this is a big one right here for us. This is what we're going to talk about right here. That the line through the point P having the direction of the gradient is what's called the normal line. So let's think about what that means for us mathematically. This is telling us that the gradient of a surface right here, this is going to give us the direction perpendicular to the surface. So this is what this is saying. This is going to be perpendicular to the surface. Now, in other words, what does the gradient tell us? It's also going to give us a direction of the greatest ascent off the surface. And that's really big for us, the steepest ascent off the surface. So in other words, like I said, it's going to be perpendicular. And we can kind of see that. So we have a few surfaces down here. And of course, the first one, this is our elliptic paraboloid. And they're saying at the point 0, 3, 6, so 0 on the y-axis, go over 3, 1, 2, 3, and up 6 on the z-axis, we will be at some point right here. And if I want to draw the gradient from that surface, well, the gradient says it's going to be perpendicular to the surface. So here's the point. And if I draw something perpendicular from that surface, that's going to be the direction of our gradient. In this case right here. And it will be perpendicular to the surface. Let's take a look right here. Here we have our hyperboloid of one sheet at the point 2, 0, 0. So the x-axis is 2, so obviously we're right here. And if I wanted to draw the normal line to this, again, draw the normal line, it's going to be perpendicular to that surface right there. Now remember, this is what's going to give us the direction of our gradient. As a matter of fact, we can actually write the equation of this hyperboloid. It's going to be x squared plus y squared minus z squared equals 4. Well, if I want to find the gradient of our function, it's going to be 2x, 2y minus 2z. Well, at that point, 2, 0, 0, we're going to get 4, 0, 0. Remember, this is saying that now notice, this is pointing off the surface. It's giving us the direction of the steepest ascent off the surface at that point right there. This is the direction of our normal line. In other words, it is the direction of steepest ascent off the surface. That's very important, like rockets. Think about a rocket taking off from Earth. They have to travel straight up. Alright, so let's look at this point over here. Here we have our elliptic cone, and we're at the point 0, 4, 4. There we are on our surface. And of course, I can get the direction. We want to go perpendicular to, if I draw my normal vector, it's going to go like this. And this direction right here, this is my normal line, which is also the direction of our gradient. It's telling me that this is the fastest way off that surface. And it kind of makes sense. It's the direction of steepest ascent, right? The steepest ascent. So it's like, okay, yeah, of course that makes sense. That's the steepest ascent. I'm not going to go at some little angle right there. And again, we can find this one. We can write the equation of our cone. X squared plus y squared minus z squared equals 0. And if I write my gradient for this, we're going to get 2x, 2y, negative 2z. And at our point, 0, 4, 4, we plug it in, we're going to get 0, 8, negative 8. Then that's the direction of the steepest ascent. And we can see this, our perpendicular. We can see this graphically as well as algebraically. Remember, and if you think about that in terms of the direction vector, right? This is my change in my x values. There's our change in our y values, and there's our change in our z values to get us off that surface the fastest. Now that's going to allow us to do a couple of things today. That's going to allow us to find, of course, the direction of the normal line. It's also going to be able to find us the equation of our normal line. And we're also going to use this to write the equation of our tangent plane. So we're going to revisit some things that we talked about vectors earlier on this year. Remember, if I know the equation of a normal line, I can find normal to a surface. I can use that our cross product in order to find the equation of our tangent plane. We did a video on that earlier. You can take a look at that. All right, the last one here we have our ellipsoid, and at the point 0, negative 4, 0, so right over here. And of course, getting the direction of our normal line would be going in that direction. In this way, we're just changing in the y direction. Alright, so go on to video number 2. We're going to start taking a look at some examples on how we can write normal lines and how we can write tangent planes. I'll see you then.